Hello, everybody. Happy Thursday to you. This will be the last time I teach you anything, unless for some reason we develop some kind of a multivariable calculus course in the very near future, and Mansfield, I get to see you again in 2 years or something like that. But aside from that, this will be the last thing I get to teach you guys, except maybe I'll have some words of wisdom for you tomorrow as well. But this will be, how about the last calculus that I teach most of you. We're going to take a look at polar curves. I'm going to try to keep this short and sweet, not get too far into this. And so I will dive right in and say the way we're going to find the area bounded by polar curves is very closely related to how we found the area underneath the curve in function mode, except instead of slicing it up with vertical rectangles, we're going to slice it up more like this into these very thin sectors, where these aren't exactly sectors because it's not a rounded part of a circle, but the smaller they are, the more closely that is a good approximation. And so just like with the area of a rectangle being base times height, where we had this very small dx for the base and the height of the function as the height, if I'm looking for the area of a sector of a circle or part of a circle, I'm just going to remind you of what that formula looks like. The area of one of these sectors, this sector with this angle theta and a radius of r, well, I'm going to find this by finding the area of the whole circle, which is just pi r squared, and then multiplying by the fraction of the circle that this angle makes up. And so pi r squared is the whole thing, but we only have this small theta value out of the entire thing, which of course is 2 pi radians. And we end up with pi canceling out, which means all we have is r squared times theta divided by 2. I'm going to repeat that again just so it makes sense in the context of the slide you're about to see. R squared times theta divided by 2. My formula looks like this. Here's my r squared, where our r isn't just a constant r like it is in a circle, but it is a function of theta. So there's your r squared. The divided by 2 is out here as a 1/2 in front of it. And then because it's not just multiplied by theta, just like with the rectangles, it wasn't just multiplied by x, it was multiplied by dx at the end of the integral. This d theta means we've got, well, let's go back here. This little tiny angle is going to 0. It's this infinitesimal angle. Bottom line, here's the formula. The area bounded by a polar curve is the integral of 1/2 r squared d theta. And then these two values, this is a d theta. We're doing everything in terms of theta, so it's from one angle to another. So tracing over the course of um, some interval of angles. And so I'd like to go through an example where we know the answer. And so I want to take a look at the curve r equals 4 times cosine of theta. And now this does turn out to be a circle with a radius of 2, but I don't think that's very obvious just looking at this equation. But r equals 4 cosine theta. Let's take a look at what this actually looks like. R equals 4 times cosine theta. So if theta equals 0, when we start at 0, we've got 1, 2, 3, 4 units away. So I'm going to say that this is what 4 units looks like. It starts here at an angle of 0. By the time we've rotated around by pi over 2, our r is going to go to 0. Cosine of pi over 2 is 0. So by the time the radar is pointed straight up, we've gotten to this value of 0. We're at the origin. As we continue along, the cosine curve between pi over 2 and pi goes to negative. So even though the radar is pointing up into the second quadrant, the curve is going back into the fourth quadrant. And by the time I get to a rotation of pi, well, cosine of pi is -1, and so we've got -4. So again, pointed to the left, but that -4 puts us right back here. Now, what this means for us is that we go through one full rotation, one formation of this circle between theta equals 0 and theta equals pi. So when I set up my area formula, I'm going to have the integral from 0 to pi. And then my formula is r squared, so 4 times cosine of theta squared over 2. And if I want to put the 1/2 on the outside of the integral, that works also. d theta. Now this integral, I don't remember how to do it. I know that I was able to do it at one point. This was actually one of the topics that I used to teach in this class after the AP test, how to deal with sines and cosines raised to various powers. But it is not something that I've done in quite some time. So I would go to my calculator on something like this. And when I plug this into my calculator, it gives me an answer of 4 pi, which is, I don't know, 12.5 or something like that, 12.56637, which is 4 pi. And that's what it should be. If I've got a circle with the radius of 2, like I've got here, pi r squared is pi times 4, which is 4 pi. So, well, I don't know if any of you were doubting this anyway, but there we go. This actually does work. Let's take a look at a different one. Find the area bounded by this curve. R equals the square root of cosine theta. When I say exact answer, that means I want to actually do this in such a way that I get a value. I want to actually anti-differentiate. And so I need to figure out what my limits of integration are. To do this, to figure out what this graph is going to look like, I'm going to think about what y equals the square root of cosine x looks like, because this isn't a graph I'm all that familiar with. And so when I look at cosine of x, I know that cosine of x is at 1 when x equals 0, and the square root of 1 is 1, so it'll be up at a value of 1. By the time x gets to be pi over 2, the value of cosine has gone down to 0, and I'm not sure exactly what the shape is because that square root's going to mess things up, but the square root of 1 is 1, the square root of 0 is 0. I'm just not exactly sure what the shape is, but it's going to have some kind of a rounded shape. I think it's going to be less curvy than a cosine function. And then after that, for values where the cosine is negative, these would be imaginary values. And so those parts don't show up on the graph. So I go backwards instead, because right now this isn't going to give us a full enclosed space. But if I go backwards to negative pi over 2, where the value of cosine is equal to 0, and then go between negative pi over 2 and pi, we'll at least get this symmetric shape. So when I think of, instead of x and y, if I think of r and theta, when theta equals 0, the value of r is 1. So we're over here at a value of 1. And going backwards, from negative pi over 2 to positive pi over 2, the value of r is going to go from 0 to 1 to 0. So it starts off at 0, rotating through the fourth quadrant to 1, and then back to 0. And so we're actually closing off a full region between negative pi over 2 and positive pi over 2. I don't even remember if this is perfectly circular. By the way, you can graph these things on Desmos. Desmos does accept r and theta for values or variables. So if you want to take a look at this more closely, go ahead and pull up Desmos. I'm just going to go with this and use this fact to find that I just discovered that my integral is going to be between negative pi over 2 and pi over 2. So my area formula is the integral from negative pi over 2, and in the course of this entire year, I believe that is the most lazy integral symbol that I have done for you. So I better clean that up just a little bit. 1/2 of r squared, since r is the square root of cosine, then squaring the square root gives me regular cosine d theta. And this is an integral that we can do. Of course, the antiderivative of cosine is sine. So sine theta evaluated from negative pi over 2 to pi over 2. And so when I start plugging in values, I've got 1/2 of sine of pi over 2. Sine of pi over 2 is 1. Minus sine of negative pi over 2. Sine of negative pi over 2 is negative 1. And I've got 1/2 of 1 plus 1, which is 1. So the value of this integral is exactly 1. Let's see. Let's do just one more before I show you the free response question that I'd like you to take a look at tonight. And that is to find the area of one petal of this shape. If you have done Any polar graphing, the graphs that are probably the most memorable are the roses. And so to figure out what this graph looks like, r times cosine of 2 theta, excuse me, r equals 4 times cosine of 2 theta. I will start off at an angle of 0. And so we'll call this distance 4 away, 4 times cosine of 0. Let's see, by the time that we've done a rotation, I know that cosine of pi over 2 would be 0. And so if 2 theta is pi over 2, that means theta is only half of that. Theta is only pi over 4. So by the time I get to a rotation of pi over 4, my radius is going to be all the way down to 0. And so that's part of it. And actually, if you're thinking about this, this already kind of tells us that if I want to do one petal of this rose, a rotation from 0 to pi over 4 is getting me half of one petal. So I could just do an integral from 0 to pi over 4 and then double that answer. I'm a little bit more curious about what the rest of this graph looks like, so I'm going to continue through. For an angle of pi over 4 to pi over 2, well, double pi over 4 is pi over 2, double pi over 2 is pi, and so we're looking at cosine values between pi over 2 and pi, and those are negative values. So on this stretch between pi over 4 and pi over 2, we're going to have negative values that are going to give us the first part of that petal, and then continuing through as we go through the rest of this rotation, we'll have the rest of the petals of this graph, and we get this kind of cool looking graph, even cooler than what I'm showing you. Oh, I really butchered that. I'm gonna have to start that over. That's what I get for drawing polar graphs and trying to talk at the same time. And this may not be as symmetric as it should be, but this graph is actually not as bad as I thought it was going to look. So we get a rose, which, by the way, if I'm naming polar graphs, I would not call this a rose, I would call this a daisy. And we would find that changing the value of this coefficient can give you more petals than what we've got. We could have 6-petaled daisies or 7-petaled daisies or whatever we want to have. But in any case, here we have my my rose is technically the name of this. And so if I want to do one petal of this rose, I could go from negative pi over 4 to pi over 4 and take care of this petal. I could go from pi over 4 to 3 pi over 4 and take care of this petal. There's lots of different ways. Or as I said before, I could go from 0 to pi over 4, get half of a petal, and just double that. Or I suppose I could go from 0 all the way to pi over 2 and get all 4 petals and then divide that by 4. How I'm actually going to do this, I don't even know. I think I'm just going to go from negative pi over 4 to pi over 4 and just do one petal and say that my area is, I'm just going to throw the 1/2 on the outside this time. The integral, again, I'm going to go from negative pi over 4 to pi over 4. I've got the 1/2 on the outside, so all I have left is 4 times cosine of 2 theta, the quantity squared, d theta. And this is another example that I would probably just plug into a calculator. Do your FNINT, plug this into your calculator and get an answer. And this is bad preparation. I haven't done this. I'm going to do this quickly. So FNINT, I've got 0.5 times 4 times cosine of 2 theta, double parentheses squared from theta equals negative pi over 4 to pi over 4. Sorry, I don't have my calculator set up on my screen to do this. I'm a little bit nervous typing this in as I am typing it. But I got an answer that leads me to believe that I did this right. I got an answer of 2 pi, which seems like an answer that would be not coincidental, or would be an amazing coincidence if it actually was a coincidence. But there we go. That's how to do these types of problems, how to find the areas. The final homework assignment I have for you is I would like you to take a look at this free response question. I will put this up, the PDF, as the assignment that I post. on Schoology. As I said with the previous one, certainly don't spend hours and hours and hours working on this problem, but I would like you to take a look at it, see what polar questions look like on the AP test back in the day when we had full AP tests. The hint I'll give you on this one is that what we did today is just part A of this problem. The rest of what we have here, I guess parts B and C are much more closely tied to what we did yesterday in this class. So that's it. Again, I'll have some closing remarks for you guys tomorrow, and maybe a little word of advice for the future, something like that. So tune in for that tomorrow. In the meantime, enjoy your day. Hopefully you're having a great one, and I will see you tomorrow. Bye-bye.